Hello, my name is Angel Marshall. I am in Chemistry 111, General Chemistry, and today I will be demonstrating the different molecular geometries using the VSEPR theory, which stands for Valence Shell Electron Pair Repulsion Theory. The purpose of this lab is to visualize how molecules form their three-dimensional shapes. According to VSEPR theory, electrons in the outer or valence shell of a repel each other because they are negatively charged. These regions of electrons, which can be bonding pairs shared between atoms or non-bonding pairs, also known as lone pairs, will spread out as far as possible to minimize repulsion. This arrangement determines the molecule's overall geometry. It is also important to understand the difference between electron domain geometry and molecular geometry because I will be discussing both of these in our examples, our molecule examples. So electron domain geometry includes all regions of electron density, meaning both bonds and the lone pairs, or lone pairs aka non-bonding areas, sorry. Molecular geometry focuses only on the arrangement of atoms. It shows the actual shape of the molecule. Just a little note, unfortunately I am allergic to latex, so I am not able to do the balloon geometry, but I was permitted to use styrofoam balls and toothpicks instead. So our styrofoam ball is going to represent our atoms. The toothpicks on the styrofoam balls are going to represent the bonds, and they're going to also help me show the bonding angles. I have these toothpicks with little pink flags that are going to represent my lone pairs for this experiment, this lab. So to begin, I'm going to go through some of the basic geometries. These ones don't really have like a group base. So when I mean group or family for this video, I'm talking about the electron domain geometry. And so these ones do not really have like a bunch of them that fit within that. So anyways, the first one is going to be the linear electron domain geometry, which also has a, for this example, also has a linear molecular geometry. And my example is going to be beryllium dichloride. Bond angle is going to be 180 degrees, and there's going to be two bonding areas, but no lone pairs or non-bonding areas. So here is my molecule, and it's beryllium dichloride. So beryllium is our central atom, and then we have two chlorides on the end, and then the bonding angle is going to be 180. Like right there. Talk about is going to be trigonal planar for both the electron domain geometry as well as the molecular geometry. The bonding angle for this one is going to be 120 degrees, and there's going to only be 3 bonding areas and no lone pairs. So, oh, I forgot to mention that linear was also in that example 2-dimensional, so it does not go off the page. Or if you know, like the window pane example, none of the atoms are going to stick out of the window pane. So going back to the trigonal planar example, this is also going to be a 2-dimensional, and it is going to form a triangle, a flat triangle, and each atom is going to have a bonding angle of 120 degrees, so 120, 120, 120. And then a good example of this molecule would be beryllium trifluoride. Beryllium's going to be in the middle, and then we're going to have our 3 fluorides bonded to it. And the bonding area, there's only 3 bonding areas and no lone pairs for this example. And then the next one I have is going to be a trigonal planar electron domain geometry, but there is going to be a lone pair. So there is only going to be 2 bonding areas, and as I mentioned, 1 lone pair. Because of the lone pairs, it is going to force our 2 bonded atoms to go down, and the angle is going to be smaller for these 2 molecules. The bonding angle is going to be smaller, so it's going to be less than 120 degrees. When I did some research, it was saying about 118 degrees, but less than 120 degrees because of the lone pair causing these 2 atoms to go down. So in the example that I have sulfur dioxide. So sulfur in the middle with its 1 lone pair, and then we have our 2 oxygens that are being pushed by that lone pair. Since our next one, we have our tetrahedral family for our electron domain geometry. So for the next 3 that I'm going to talk about, these are all going to have tetrahedral electron domain geometries, but the molecular geometry is going to change based off of how many lone pairs it has. So for our first example, it is also going to be a tetrahedral molecular geometry, and it is going to have 4 bonding areas. And a good example of this is going to be CH4. This is when we start to see our 3-dimensional molecules as well. So if you've heard of like the window pane or like the piece of paper example, like just imagine like this is slicing through. Our central atom is going to be within the window pane, so it's like attached to the window pane, and then this atom, so like in this example, CH4, so this hydrogen is going to also be a part of that 2D model or attached to the window pane. And then this hydrogen is also going to be attached. And I'm trying to fix this while I'm explaining it. So these are within the window pane, these three. And then we have these two atoms, which are also hydrogens because of CH4, that are going to they're going to be sticking out of the window pane. So this one's going to be sticking out like towards us, towards the screen. And then this one's going to be sticking out away. So now it's a three-dimensional shape. And the bond angles for this is going to be about 109. I found 109.5. This says 109. So I would stick with 109. And then if we were to take out one of the bonding areas, we would have a lone pair right here. And this lone pair would cause our bonding atoms angle to be pushed further down and closer together. Oh, excuse me. And so the bonding angle would be less than the 109 or 109.5. And I found about 107 degrees. And so this would change the molecular geometry to a trigonal planar. And a good example of this one would be NH3. So our nitrogen would be our central atom, and then we would have one hydrogen that sticks out of the window pane, one hydrogen that's going the other way, and then these two would be within the window pane. And then our lone pair would also be in the window pane. And then lose another bonding area and gain another electron, gain another lone pair and lose another bonding area. We would have an electron geometry of that is called bent, because the two lone pairs are going to force our atoms to go even closer together. And a good example of this one is going to be H2O. And so, like I said, the electron domain geometry for this one is going to be tetrahedral, and then the molecular geometry is going to be bent, and then the bonding angle is going to be even lesser than the trigonal pyramidal, which is bent is going to be even less than that, so less than 109, or what I found was 104.5 degrees. Talk about is the trigonal bipyramidal family for our electron domain geometry. So there is going to be 4 examples of this, and showing how the molecular geometry changes with the lone pairs. So the first one I'm going to talk about is going to be trigonal bipyramidal for both the molecular geometry as well as the for example, there's going to be 5 bonding areas and no lone pairs. This molecule forms a trigonal bipyramidal shape for both the molecular geometry and the electron domain geometry. For my example of this molecule, I have phosphorus pentachloride, and this is not straight at all. Imagine that is 90 degrees. All right, so as I was talking, for this example, the phosphorus chloride, phosphorus is the central atom, and then we have 1, 2, 3 chlorides that are going to be attached to the window pane, and these are going to have 90-degree angles. Sorry, these are 90-degree angles, and then the ones that are going inside and outside are all 120. And those are all, these are chlorides. Chloride, 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 chloride. Have 4 bonding areas and 1 lone pair. We will make a seesaw molecular geometry. Wrong one. A seesaw molecular geometry. And the lone pairs are going to force our three-dimensional shapes, our three-dimensional atoms to be even closer together. So they're going to be less than 120 degrees. And our top and bottom one are also going to be forced, and they are going to be less than 90 degrees because of this lone pair causing repulsion force. And a good example of a seesaw molecular geometry is going to be sulfur tetrafluoride. So sulfurs are going to be our central atom, and then we have fluoride on the top, fluoride on the bottom. These are going to be in our window pane with our central atom. And then these 2 fluorides are going to be inside and outside the window pane. And then if we lose another bonding area and we form, have 2 lone pairs, we will lose another bonding area, and we will have 3 bonding areas. And this will cause our molecular geometry to form a T-shape. And our T-shape will look like this. So our lone pairs will now be the ones that are sticking inside and outside the window pane. And these will be all attached to the window pane. And a good example of this one is going to be chloride trifluoride. And the bonding angles are going to be, pairs are going to force these to be less than 90. So I should probably make this go that way a little bit. That way it looks less than 90. So yeah, less than 90 degrees because of our lone pairs causing them the atoms to go closer together. And then our next one, if we have 3 lone pairs, we will have only 2 bonding areas. And the 3 lone pairs are going to cause our bonded atoms to be forced, like they're going to have a repulsion force that is going to force the bonding angle to be 180 degrees between the bonding angles. A good example of this one is going to be xenon difluoride. As you see, we have our 2 lone pairs that are going inside and outside the window pane. These are all embedded in the window pane, and this is embedded in the window pane as well. The electron domain geometry is what I'm talking about when I talk about the octahedral family. Oh, any of the families that I just talked about. So the next 3 are all going to have octahedral electron domain geometries. This first example is also going to have an octahedral molecular geometry, and there are going to be 6 bonding areas and no lone pairs for it. And the bond angle is going to be 90 degrees between the molecules. That is 2 pyramids together, where the bases are stuck together. And the octahedral molecular geometry is going to be sulfur hexafluoride, so SF6. So there's going to be 6 fluorides. So 1, 2, 3, 4, 5, 6. And so, like I was saying, if our window pane, if our central atom, which is our sulfur, is embedded into the window pane, this fluoride and this fluoride are also embedded. So this is our 2-dimensional part of our molecule. And then these fluorides and these fluorides are going to be our 3-dimensional parts. So these ones are going to be outside, and these ones are going to be inside the window pane. And the bonding angle between these is going to be, and then our top and bottom is 180. So 90 lone pair instead. The lone pair would force, of course, our atoms to move closer together because of the repulsion force. So a good example of that would be bromine pentafluoride. Let me find a good one. The next molecular geometry shape that we're going to talk about is square pyramidal. It's still within the octahedral electron domain geometry family that I was talking about earlier. And so with this one, we have 5 bonding areas and 1 lone pair, pentafluoride. And it's going to have a lone pair, it's right here on the bromine, and it's going to bond to fluoride up here, fluoride, 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 fluoride. Sorry, fluoride, 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 lone pair, fluoride, fluoride. And because of the lone pair, it is going to force the bonded molecules to get a little closer. So it's going to be more, less than a 90-degree angle for the bonded. The next one I'm going to talk about for the molecular geometry within the octahedral electron domain geometry is our square planar molecular geometry. And a good example of that is going to be xenon tetrafluoride. And there is going to be 4 bonding areas with 2 lone pairs, and are going to be coming out the top and the bottom of our central atom. And so for this case, our central atom is going to be our xenon. And so our fluorides going inside and outside of the window pane. Because of our lone pairs, they are going to force the 90-degree angle the bonding angle to be 90 degrees because we have it at the top and the bottom, so it's going to be 90, 90, 90. There's 4 bonding areas and there's 2 lone pairs, and that causes the bonding angle to be 90 degrees. And a good example of that is xenon fluoride. Xenon is in the central atom, and then we have our 2 fluorides here, 2 fluorides there, and this is going to be a 3-dimensional shape. Our